Hello everyone, February the 4th. Alright, let's get to it. Huh, damn. Check if one string swap can make string equal. Two strings equal length. A string swap is an operation where you choose two indices in a string unnecessarily different and then swap the character at these indices. Return true if it is possible to make both strings equal by performing at most one string swap on exactly one of the strings. Two indices and then swap the character. If it's possible to make both equal by performing at most one string swap on exactly one of the strings. What do you mean by exactly one of the strings? You have to do on both, right? Oh, the string swap. Hold on, let me read it again. Choose two indices in a string and then swap the character. Oh, so you do the swap in one string. At most one string swap on exactly one of the strings. So you do either don't swap, right? Or you do swap, then you swap on one of the strings. And after the swap, it has to be the same as the other one. Okay. Oh, it doesn't matter which string you swap because I can just swap here to get there as well, right? So it doesn't matter, which means we can go through the string, right? Do the comparison, and the first one that's different. So we should have only two differences, right? That's for sure. Two differences, because if we have more differences, then if we have too many differences, like 3, then it doesn't work because we need to swap more. Because if you only allow one swap, that basically means only 2 of them are different. So you go through them, you mark where they're different, should be 2 positions, so you got 2 indices, and then you try to see if you swap them, are they the same, right? It's not really swap, you don't even have to swap, you should do a cross to compare if they're the same. If they're the same, then it's possible, otherwise it's not. Or you don't get any differences, which we can actually eliminate that situation at the beginning. Okay, how do I tell whether 2 strings are the same? Determine whether strings are equal. I think we probably have to use compare. So I think equal would be fine. Okay, so we just do equal then. So hold on, let me first clean this thing. We say if S1 is equal to S2, return true. Alright. Otherwise, then we can say int low and high. Okay, for I 0 smaller than S1 dot size I plus if alright, so I should be -1. This shall also be -1. Alright. If S1I is not equal to S2I, okay. If low is smaller than 0, low equal to I, else if high is smaller than 0, high equal to I, else return false. Once we're done, we'll return S1 low shall equal to S2 high and S1 high equal to S2 low. They have to cross equal, basically. Not sure if this is necessary, but safety. Let's do this. Okay. Give this a shot. Actually, we should also write this. $17.90. Oh, check. Record the indices where S1 and S2 differ. If there are more than 3 differences, more than 2 differences, return false. Otherwise, oh, what if only 1 difference? If they have 1 difference, that's a good question. What if they have only 1 difference? Then it shall be false, right? Then, but mine couldn't do because it has -1. It's actually compile error. There we go. If there are more than 2 different, more than 2. If there are more than 2 or less than 2 differences, return false. Otherwise, we basically check whether a swap would make the 2 string. A swap on the 2 indices would make the 2 strings equal. So we'll check this. So it's only going to be 1. So at the end, we shall check high is larger or equal to 0, right? And this. If high is smaller than 0, then that it should short circuit. Okay, let's try. I believe it will short circuit. Yep, I think it does short circuit. Okay, that's pretty good. Frequency map and check difference. Only check difference. They use number of diff. That's fine. You can use number of diff. Oh, you already set to 0. Then you don't have to consider. Yeah, that's fine. Okay, so we got this. I think we should start writing this. We really should start writing this, even though it can be a little bit tricky. At least get like a skeleton done. 3, 4, 1, 0. Actually, I'm not sure if I have this. Nope, I do not. I don't think so. Yeah, I do not think so. So we go copy. Alright, so let's do this segment tree. We will use segment tree. Alright, so segment tree. Let's see, class seg tree. Okay. What do we need for segment tree? We need an n, which is the length of the numbers, right? Okay. And self dot tree, and then we start with values. How many do you need? And each one requires a few things. So okay, each node contains 4 values. So the 4 values are total sum. No, we say max subarray sum, total sum, max prefix sum, max suffix sum. Okay. As follows. Alright. Are they all larger than 0? Now larger than 0. So max sum was set to 0. Ugh. Maximum 0 minus math.inf. Total sum is 0. Max prefix sum, max suffix sum. So we also need self.n equal to n for this in range. This is important. I believe if you have length of 5, then you need, there's a little bit logarithm going on, because we know the last one have to be at least this much, right? And for 3, we'll have I think it's. Oh. Oh, I forgot. How's the segment tree? So we have a segment. Right, we have a segment. Breaking in half. Breaking in half. Eventually, we have individuals, right? So it has to be this, right? 1 plus 2 plus 1 plus 2 plus 1, 2, 3, 4. So this has 7. So no matter how much we have, I think I do a log 2n, right? Because if you do a log 2 on 4, you get 2, right? Log so log 2n, we will ceiling this thing because log 2 is 1, log 2 3 is 1 point some stuff, right? And up until log 2 4. So whatever this, then we do 2 to the power of this. Actually 2 to the this one plus 1. So 2 to the power of log 2n plus 1. So probably need to compute the tree size. I think it's going to be 2 to the power of int. Int probably is not right. So mass dot ceiling of mass dot log 2 n plus 1. And this is going to be tree size. All right. We'll stop right here because I need to feed my cat. All right, let's eat. Yes. 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 All right, I'm back. Let's segment tree this. So we have segment, we have the tree, we have the, now we have everything. And then I think there are two functions. One is called update, right? So basically we want to update this position into the tree. So we'll deal with this later. And then we also have update and query. Query, basically you have query start and a query end. I have a query start and query end. This one will return this. So basically this will return, what does this query return? Technically it should return all four of them, which means I think this has to be a list of int, right? Because we need to return basically everything in it. So we also wait to implement this. Okay, now we need to do update inside. Alright, so we basically we have index and we have range left. Ah, that's what I used to do. Range left to range right. Not return anything. Okay. So not start and end. We'll do left and right. Okay. Alright, so update. So when we do this, we basically call self.update. Index, so range left is always 0. Range right is always n minus 1. Alright, so that's that. That's the range. And now we do this. Right, okay, we have index. Don't you need value? Oh, I don't really need value because I think I can put value inside. Oof. What did I do? I think, oh man, I don't even need, I can just put, let's do this. Nums, right? We do this as a self.nums equal to nums. Self.n equal to len nums, right? And we use self.n. Okay. So now we have index and we also have the nums inside. How do we update? Well, we update first, we check, we calculate the mid. Alright, mid will always be range this then divided by 2. And then we say if it's on the left hand side, then we update the left. If it's on the right hand side, right, so say if index, because mid is going to be included in the left. So if index is smaller or equal to mid, then we do self.update index range left and mid, right? Else we do self.update index range mid plus 1 range right. Once we're done with everything, and we have a bunch of more to do, but what's the anchor condition? Anchor condition is if, because at the end what we're gonna have is range left and range right is different by only 1, right? And then we keep going, and then and then like 1 and 2, so the mid will be 1 and the other will be 2. I mean, it's fine, because if we keep going on, one of them will be, yeah, it's so essentially it depends on the index. So if range left is equal to range right. That's when we hit the bottom, right? That's when we hit the bottom, if they're equal. So when they're equal, we go down to the bottom, then we just need to update every single thing, right? We update every single thing because you're a subarray of size 1, so your max subarray sum, total sum, prefix, suffix, they're all the same. Ooh, so how do I update all the values? Oh, we can say for I in range 4. Holy crap! Where's the node? Damn, I forgot the node. Ugh, node. Screw me. Node should be 0, right? And we basically say self.tree node I will equal to self.nums index. Okay, so once this is done, we just return. We're done with this. Ay, ay, ay. Alright, the cat did something bad, as usual, but it's fine. Alright, so a complete binary tree. What is the left node? If I start with 0, right? So left will be, the left is 1, right is 2. So left is 2 times, so left is 2 times node plus 1. Right will be 2 times node plus 2, right? 0, 1, 2. 1 will go to 3, 4. And 2 will go to 5, 6. Yeah. Okay. So blah blah blah. So now, after I update the left and after I update the right, now I need to update myself. So I have a left and I have a right. So for first things first, we say self.tree node, right? 0, that's the max sum. Okay, we do it later. This shall be self.tree. Let's do left node. Node left. Left node. Left node, right node is 2 times node plus 1, 2 times node plus 2. So here I can just say left node. This I can just say right node. Okay, so this is going to be left node 1 plus self.tree right node 1. So this is total sum, right? So we have the total sum. Now we also need a prefix sum on the left, right? The prefix max prefix sum will equal to, so max prefix sum, right? So we have here, and then we have here, and then we have here. So I want to know the max prefix sum, which is the total sum plus the max prefix sum on here, right? It's a total sum on the left and the maximum. So hold on, this is a comparison. So it's either the max prefix sum of the left, right? Or it can be, like if we want to extend past this, then we need to take the total sum plus the max prefix sum of the right. Okay. So where are we? Say self.tree node 2, right? Shall be the maximum. Self.tree left node 2 or self.tree left node 1 plus self.tree right node 2. So this is max prefix sum, right? Now we do the same thing for 3, which is the max suffix sum, right? So self.tree right node 3, this is the right node's max suffix sum, or we say self.tree left nodes 3, which is the left node's max suffix sum, right? And this plus self.tree right node, we need the total sum of right nodes, 1. Okay, so we call this as a max suffix sum. And can we do self.tree node 0? Okay, so the subarray sum. So the max subarray sum is going to be a maximum of multiple things. For example, it can be the max of the left, so the left node. It can be the right node, so their maximum subarray sum. Or it can be the crossing, right? So it can be the crossing. So if we want to do a crossing, so basically we'll take this part and take this part. So we can say is the max suffix sum of the left plus the max prefix sum of the right, right? But here is the thing. Here is the thing. What if someone is negative? Have you thought about that? Because I am calculating the max sum here, right? I didn't really care if it's positive or negative. But if the max of, like if everybody here is a negative value, right, then the max sum will be the first value, which is a negative, right? It's a negative value. Or maybe we have a bunch and then we have a positive and then we add them together. Anyway, it's a negative, right? It's a negative. So here, it might also be a negative max suffix sum, right? It might also be a negative. So when this happens, right? When this happens, you obviously you don't add them together, right? So you need to pick. Oh, so you need to pick the larger of the two. Maybe we can do that. Maybe we can say, you know, it's this or this. So maximum subarray sum, maximum subarray sum. Do we do the max prefix sum and the max suffix sum? Yeah, I think we should. Because you add them together is not necessarily making any bigger, right? Sometimes you maybe don't want to add them together. But I was wondering, if I already consider these two, do I need to also compare the max prefix and max suffix? I mean, let me think again. So if I have, I do believe, maybe I don't need to. Because if the max, so think about this way, if the max subarray sum is, the max subarray sum will not be smaller than the max prefix or the max suffix, right? If max subarray sum is smaller than these two, then our max subarray should be one of these two, right? So the max subarray sum is always the biggest, okay? It's always the biggest. And because I already find the biggest, so these two shall work, which means I think I can go ahead and then just add them together. 0, 1, 2 plus self.tree right, and then 2, right? So this is like this. You see, seems like we are forcing the prefix, and okay, this is not right. This is going to be left need a suffix sum, right need a prefix sum. You feel like you're forcing to add them together, but it doesn't matter because you add them together, it might not be big, and it can be remedied by these two. Okay, so by doing all this, we're good, right? This is the update function, and everybody shall be updated. Let me just mentally compute one of them. Let's say the leaf level, right? On leaf level, I have just 2 numbers. Okay, I have 2 numbers, and total sum, I'll add the total sum together. That's good. And max prefix sum, I will select the left, or I want to add them together, or right, or suffix sum the same, right, or we add them together. Okay, and the cross sum, I can do this, or I can add them together. Okay, I think it should be fine. So now it's query again. Query, we need a helper function as well. So query, right? So query, I just need a range left, range right, and query left. So we do query left, query right, range left, range right. Of course, also node index. This shall return a list of integers. Oh, we don't have to do list of integers. I can just return integer. I don't know why you want to return a list of integers. Just integer is sufficient. Okay. So query left, query right, range left, range right. What is the condition? Well, the condition is hold a second. We don't need to do this query because we're not querying a range. We're querying. I don't think this is necessary. Alright, this is a segment tree, and then query, I don't need a range left, range right. I don't need this. I don't think so. Because I just need the maximum subarray. I already computed. Okay, so we say seg tree, seg equal to seg tree. I just put nums in it. Okay, that's fine. And then I will update it. Right, so for index, I don't think I need index. Why do you need index? Why do you need index when you do the update? When you do update, you just do the values, right? I mean, let me think again. Well, you do need index because the index help you decide if it's on the left side or right side. Okay, that makes sense. So for I, in range, let me do this, n equal to len nums, right? So in range n, yeah. Then we say sec.update. Okay, update index. That's it, right? The external facing is very simple, right? Very, very simple. Range left, range right. Yeah. I think it makes sense. And we'll do that. Once we finish this, I kind of want to run it just to see if this one works. You know? Let's run this. I'm just curious, because this is a very big undertaking. I think it's necessary to go through this. Oh my goodness, to go through this very carefully. Right, we want to do this very, very carefully, so we don't want to redo anything of that. So this one, the output is 7. Doesn't matter the output. At the moment, I have what I want to do. This is going to be max subarray sum. This is shouldn't be nums. Yeah, it should be nums. Okay, nums. Alright, doesn't matter. What I want is to print. I can return sec.tree 0. What? Because I did not specify what this is. List of int. Huh. Oh wait, hold a second. Oh, I see. Yep, that's wrong. There should be 0 and 0 is. Screw this. I want to print out the whole thing. Sec.tree 0. Incompatible. Got float. Expected int. Dude. 10 to the 6. Oh. How do I int this? Well, maybe I can just, I don't know. Or, yeah, no or. Let's just give this a shot. I'll come here and then we just call Python 3 2025 02. No, that's not right. LeetCode. This is which one is 3410? So what we get is 4004. 4004. Okay, let's see if this is 4004. So what I want to find first of all is -2, -1, 3, -2, and 3. So the easiest to check is the second one, which is the total sum. What's the total sum? This is 0. -3, 3 is 0. Oh, it is 0. Total sum is 0. That's good. And max prefix sum. Max prefix sum. We have -1. -1. This is -2. Right, -1, -3, -4, -1, -0. Yeah. Max suffix sum is gonna be 3, 4. Yeah, it's gonna be 4. Max suffix sum is 4. Max array is going to be 4. I believe it's going to be this part. 3 - 3. 3 - 2, 3. That's the part. Okay. Looks to be okay. So now let's do this. How do I do this? We need to build up the indices for each value. So I need a default dict, which is gonna be value, so num to indices. Okay, that's gonna be default dict. I don't think I have default dict. So from collections import default dict. Then what? So it's gonna be a default dict of list. Ooh, I can do both at the same time. Then we say num to this ni. Okay, that makes more sense. I believe it's gonna be enumerate. I haven't written this for a very long time. I probably don't even need this, right? So this I already have. It's gonna be n dot append I, right? Okay, so that's that, right? And then we're gonna brute force by removing, right, each number, each unique number, find the max subarray sum, keep track of it. Oh, that's not called brute force. This is backtracking, right? Backtracking and add the number back. Okay, so essentially, when you remove it, you're setting it to 0. Oh, be very careful when you say set it to 0. Because you set it to 0, then you have 0, right? But you're not supposed to have 0. So when you set it to, oh God, when you set it to, when you remove it, you need to set it to minus math.inf. That's what I think you should set. I do believe that's what I need to set. So basically we say for key value in num2 index.items. So remove key first. Remove key at each position. Let's change it. N indices, right? Remove value n at each index. So here we're gonna do another. So for I in indices. So what we're gonna do is sec dot update, right? We're gonna update index is gonna be I. Ooh, that's why you need the value put in. My bad. So, god dang it. How many times do we use self.nums? Only once. Yeah, so this is not necessary. This is not necessary. All we need is just n. That's it. So the original idea is right. And here we need index. We need val. Okay. So this would just become val because I want more control on what val to set. And index val, here same, index val. And this is gonna be, hold a second. Oh. That's my cat being naughty again. So index, what's the val when you update? Oh, so the update I need a val as well. Okay. So we have index, we have val. Perfect. So this is going to be randoms. This is going to be n. Okay, so now here we're gonna pass in math.inf. Ooh. Damn. What about the sum? If you do minus math.inf, lordy. Okay, so we need to change. We need to change. Oh God. I put this as, oh, that's fine. So we do that. And then we say if val is equal to minus math.inf. So this suggests that it's a reset, right? So this is indicates removal of val at index. So self.tree node, when that happens, then we'll set 1 equal to 0, right? Because you remove it. This position is just plus. You always plus. Okay. Oh. Oh God. Oh Lord. Oh. What is does Python has a maximum concept for integer? Python max integer. Probably not, but sys.max int. Really? Is that the one? Yeah, it's unbounded. Yeah, you can use this. Gordy. 1, 2, 3, 4, 5, 6, 7, 8. All right, so we can do the minimum. So if everybody is 10 to the minus 10 to the 6, then we have 10 to the 5th of them. So essentially, this is gonna be 10 to the 5th. All right, so it's minus 10 to the 11th. Okay, let's set the true max. Okay, let's set a true max. Max, we set it to 10 to the 11th power, 12th power. How about that? Okay, and everybody is going to be math.inf max Okay, so here is the same. Let me do this. Max is 10 to the 12, and then math dot this is going to be max. All right, now that makes more sense, right? And number 14 need to change because this should be max is not defined. Jesus. All right, I'm gonna be very unhappy. Oh my God. Self dot. It's also self dot. All right, what else? This is self dot. Okay, so remove value. Okay, so we remove this. And we remove everybody. Once we remove, I need a result is minus max, right? Because we want to find the maximum. So res equals to max, res and a seg dot tree 0 0. This is the current, and now we're gonna backtracking by putting everybody back. So we say again for I in indices seg.update I, we will put the value inside. So we're backtracking, and then we go to the next one because we only allowed to remove one, right? Any integer, remove all the occurrences of x at most once. Oh, at most once, which means you can also not do it. God. Oh, if you're not doing it, then they must all be positive. Ah, I see. It must all be positive. So I shall get seg.tree 0 and 0, right? So the initial, without removing anything, we get it. And then we remove 1. We shall do this. So basically we say if seg.tree 0 0 is equal to seg.tree 0 1, right? Then we just return res. So this is the situation. Hold on. This is very interesting, right? So this is the situation that all elements in nums are positive, are non-negative. Right? When that happens, you just add everybody up. You don't remove anything. You add everybody up. That will be your result. Otherwise, you need to at least remove the negatives, right? So you try to remove. Maybe we can even say, why would you remove positive values? Right? You won't remove positive values. So we can also say if n is smaller than 0, right? That's the only one that we want to remove. If it's smaller than 0, then we remove, right? Remove value at each index. So we remove all of them. Once we remove all of them, we update the result. If it's positive, we just don't remove anybody. It will remain the same. And then at the end, we will return res. Oh boy, how do we do? We run a test. Okay, the first one pass. All right, let's see. Let's see if this one pass. All the test cases. What happened? Oh, good. We passed all the test cases. Dare we try? Let's do one more. How about we do one more? Like that. So kind of edge cases was trying. Okay. Looks promising. Alright. Hold on, let me write a bit more. Use segment tree. Each node in the segment tree records the max subarray sum, total sum, max prefix sum, and max suffix sum. Right? We can always use these values of the two children to compute them, to update them in the parent. Also, the segment tree only needs to implement the update function because the value we want has already been computed inside each node. I believe it will cost O1 log n to run this because it's O(n) right here, and segment tree always running log n. Oh, is it log n or yeah, it is log n, right? You're running log n, and here it's the same because each indices we go through once. Well, you can technically say we go through twice, but it's the same. Okay, it's time to submit it, and we see how that goes. Run one more time, just make sure we didn't make any stupid mistake. Okay, look good. Submit. Oh, it's slow. Oh, it's slow. No. Oh no. Oh no. Okay, actually it's not that bad. We passed 638 test cases and one of them failed, which is good, and it's not too big a test case. So I think we can debug this and see what happened. Output 265 should be 309. What's the total sum of this? Actually, I'm a little bit curious. So I'm not doing a full out debugging session right now, but I'm just curious. So we have, I don't know, 7, 12, 23, minus 1, minus 30, 31, 5, 14, 49, 6, 35, and break it, 44, 26, 25, 41, 47, minus 23, 12, and 49. So what's this? 7, 12, and 23. This is 42. What is this? This is 31, 5, 14, 49, 6, and 35. This is 140. This is 20, this is 26. This is 25, 41, and 47, which gives you 113. And the last one is 61. Okay. Okay. How do you even get to 309? What in the world? How do you get to 309? What is 309? Did I do something wrong? I couldn't see how 309 is even computed. Let me read the question one more time. Choose any integer such that nums remains non-empty. On removal, all occurrences. Ooh, there's also another situation I think I didn't consider. Oh, I think I considered it. Okay. Remove all occurrences, return the mass separate sum across all possible resulting arrays. Right? You remove one value and then you try to get it. So here, if I remove -1, it will be, oh wait, hold a second. I know. So you have to add them together. Okay. Oof. So when you remove a value, okay, let me see how much we are missing here. 309 minus 265. We're missing 44. We're missing 44. Now we're missing 44. We're included 44 in this. Let's see. 26 plus 113 plus 61. That is 200. Right, plus 140 is 340. Plus 42. The total is 382 without any of the negative values. I don't know. $265 is the total. When you put everybody in it. So you're telling me that by removing some negative values, I mean, oh wait, hold on. Yeah, no, it's reasonable. I think it's just the removing thing. Probably the removal was not well considered. Alright, I feel like this is still a little bit too much to work with. Maybe what we can do is, I don't know, we'll run it, maybe we cut it in half, you know, or cut it in the other half. Just try to see. Nice. So both 7 and 8. At most I can use 9. Holy crap. Huh. So the 9th one will never be used. Okay, so now we have a much smaller one. Ooh, now I wonder. Now I wonder. Yep. It doesn't work. That's fine. This is much easier to work with. And in fact, it's very straightforward. It's just the first, not including 35. I said I don't want to debug, but I'm actually debugging it right now. I have 7, 12, 23, minus 1, minus 30, 31, 5, 14, 49, and 6. Again, this is 42. This is 140 minus 35. It's going to be 105. Right? And what is my answer to this? Let's run this. So my answer is 116. So the answer shall be 42 plus 105 minus 1, 146. I gave 116, which is minus 30, I think. Ha! Huh. No way. The answer I give is the entire thing, which means I remove minus 1. I get 117. And it's not even considered. Alright, something is seriously wrong. Okay, something is seriously wrong. But in general, we are in the right track. So let's debug it tomorrow. And I believe this one we can debug it. We can surely debug it. I think what I'm gonna do is I'm gonna take a deeper look into each splice. In fact, I think we can even reduce it further. We can probably reduce it like this and this. It's my guess. Ugh, darn it. Okay, so it's too aggressive. And let's remove just one of them. Good. So this is even more distilled, which is 12, 23, minus 1, minus 30, 31, 5. Okay, this is a good example. So we'll deal with this. 6 values, not that bad. We can list out everything. Okay, that will be it. Right? It just doesn't make sense. I'll see you guys tomorrow. Adios.